So the next talk is also a distinguished paper about data race detection, dynamic data race detection, and the talk is given by Minjian Zhang.
Hello. Thank you, David, for the introduction. Good afternoon, everyone. My name is Minjian, and thank you all for coming. The talk today will be on our project, Dynamic Risk Prediction with O1 Samples. This is a joint work with my friend Mosaad, Professor Umang Mathur, and my advisor, Professor Mahesh Viswanathan. Okay. And the talk is structured with 4 sections. Firstly, I will be going through the background, then discuss happens before risk detection, and mention some previous sampling schemes, and eventually run into our contribution. Okay. So the setting of the talk will be dynamic analysis for data risk detection. Dynamic analysis is one of the go-to techniques, which basically means that for a given program, we are going to instrument the program, run it, and observe execution traces. The analysis will be done on the execution traces rather than the program itself, and we declare the risk or risk freedom based on our observations. Okay. The problem we are trying to solve, namely happens before risk prediction, is one of the kind. So happens before relation is a transitive relation that orders events of an execution in the following way. It firstly preserves the thread order, and then it preserves the order between critical sections. So namely, the release of the earlier must happen before the acquire of the later. And in this talk, we assume 4 types of events, namely the release and acquire of logs, and the write and read from memory locations. Okay. And happens before relations can define data races. We say that there is a race if conflicting events are not ordered by HB. And 2 events are said to be in conflict if they access the same memory location. They're from different thread, and at least one of them is a write. So in the example here, the 2 writes are in conflict, but they are not in race because they are ordered by happens before. Okay, happens before races are easy to detect. There is actually is a linear time algorithm that runs in one pass for the existence, and one classic example is the vector clock algorithm. The state of the the state of the art algorithm that soundly detects all happens before races is fast track. Fast track is improved from the vector clock algorithm, but runs much faster in practice. Okay. So thread sanitizer is an industrial tool that basically implements a variance of fast track. Its official document reports the average slowdown from 5x to 15x, and an average memory overhead from 5x to 10x, which basically means this algorithm is only suitable for in-house testing, but may not work well on large-scale softwares. And one possible solution for this condition is sampling. The informal idea behind sampling for risk detection is that we only want to analyze or observe a small set of events to detect data races. It is known that sampling can effectively reduce the overhead of fast track. And one typical example is PACER, which is a state-of-the-art sampling technique for dynamic analysis. And the PACER can reduce the overhead of fast track from 5x, say, to 50%, 52% with a sampling rate that is low enough. Okay, but before I'm going to talk about how these sampling schemes really work, I would like to emphasize the importance of soundness for sampling risk detection. Soundness basically means every risk reported must be a real risk. This is because that the false alarms are very hard to verify, as the concurrent programs are meant to be non-deterministic. Okay, and when we are sampling, missing HB edges between threads can actually lead to false alarms. So in the same example, if we're going to miss the red edge there, we could be falsely claim there is a risk between the 2 of writes. Okay, and a general framework of sampling. So in general, any sampling technique for HB risk detection is expected to be a streaming algorithm that satisfies the 3 properties here. We discussed soundness And a small sample size usually means a good running time. And we also require a good mathematical guarantee for the algorithm to make sense, because we can always construct a trivial algorithm that samples nothing and reports no risk, but satisfies the first two properties. And we observe that we can roughly understand how each sampling technique satisfies the three properties by asking two simple questions. The first one is which acquires and releases will be sampled. This tells us how the soundness is preserved, because we can look into how the edges between threads are observed. And the second question is basically which write and reads will be sampled. Okay, so let's go to the first scheme. Say that I have an execution, and the first thing I'm going to do is to simply sample all the synchronization events. So I'm not going to miss any of the edges between threads. Then I'm going to sample each read and write event with a probability of p. This in some things give me a shorter trace, and I can run fast track on it and declare a risk if I find one. Okay, so basically this scheme samples theta n many events, and the probability of detecting each risk is p squared, and this is their mathematical guarantee. The tool that built upon this idea is light race. Okay, and it turns out that we can improve the mathematical guarantee here by sampling slightly more. So let's go to the second scheme. For a given execution, again, I'm going to sample all the synchronization events. But now I'm going to sample each read and write event as a potential first event of a risk with probability p. Then I'm going to sample events to confirm my guesses. Okay, this again gave me another shorter trace, and I'm going to run fast track. Okay, and similarly, this scheme samples theta n many events, but the mathematical guarantee is that the probability of detecting each risk is improved from p squared to p. Okay, and this is basically the naive version of Pacer that without any optimizations. Okay, and we observe that the previous schemes we mentioned, they all sample theta n many events, which could be a bottleneck. And in practice, Pacer reduced the large overhead of fast track to 52%, which is amazing. But we want to know if that's the best possible. And can we actually achieve a lower overhead by sampling sublinearly many events? And our answer is a one-sided property tester. So a one-sided property tester is a randomized algorithm that meets the following two obligations for a decision program L. Okay, the first obligation states that whenever the input is in the language, the property tester must always answer yes. And the second obligation requires that it answers no with high probability when the input is far away from the language. And when we say that the input is far away from a language, we mean that it is very different from every member in the language. Okay, and please note that a property tester does not approximately solve the decision program, because it has no obligation to answer yes or no when the input is not in the language, but also not far away from the language. Okay, and this actually allows us to build efficient algorithms, say sublinear algorithms in many fields. And if we want to generalize the idea into risk detection, the first question we have to solve is to define the decision program. Here we pick L to be the set of executions that are HB risk-free. And please note that we cannot take L to be the complement, although it might be more natural. If we take L to be the set of executions that has at least one HB risk, the first obligation of the property tester will require us to build an algorithm that always answers yes whenever there is a risk. But no sublinear algorithm can ever do that. And in fact, only deterministic algorithm like fast track has this power. Okay. And then a one-sided epsilon delta property tester for L is basically a randomized algorithm A, such that on any execution, if X is risk-free, it reports no risk. If X is epsilon far from being risk-free, If we report a race with probability 1 minus delta. Okay, and here we use the Hamming distance to measure how far away an execution is to the set of risk-free executions. The Hamming distance basically measures the number of different events between executions of the same size. It is not defined over executions of different sizes. Okay? And therefore, we propose the following naive but powerful algorithm, which we call RPT, namely the risk property tester. Okay? And the first thing we do is that we are going to uniformly sample R subtraces of length k. And please note that by sampling in this way, we are going to miss happens-before edges between threads because we are not going to observe all the synchronizations. And therefore, we are going to analyze each subtraces independently. We are not going to declare any risk cross sections. Okay? And we report a risk if any of these subtraces has a risk. And this algorithm basically samples R times K many events. And it turns out that we can set the value of K and R based on the number of threads and the maximum number of logs held at any time to make this algorithm a property tester. So more formally, our theorem states that let M be 2t plus 2h, where t is the number of threads and h is the maximum number of logs. For every possible combination of epsilon and delta, we can set k and r to be the following values to make RPT a one-sided epsilon delta property tester. And this means that if we take the number of threads and logs to be constant, RPT is sampling constantly many events. And the insight of our theorem is basically that in order to, in some sense, approximately determine HB risk freedom, the number of events we need to observe depends on the parameters of the execution rather than the size of the execution. Okay? And it's actually not easy to prove the naive algorithm is indeed correct. And most of our technical sections is occupied by the proofs, and all readers are encouraged to take a look. Okay. Experiment. So we implemented our 2RPT as a property tester that takes epsilon equals to 0.01 and delta equals to 0.1. This basically means that we expect the property tester to behave really well when namely have a 90% of report at least one risk if we need to change at least 1% of the events to make the execution free. To make the execution risk free, okay? And we compared our two against fast track and pacer. And it's important to realize that this is not a like-for-like comparison because RPT is a property tester whose behavior is completely determined by the parameters, while pacer and the fast track, they are traditional risk detectors. Their behavior is determined by the size of the execution, and the goal is to detect as many risks as possible. But for RPT, the goal is to answer a decision problem. So the main goal of the experiment is to understand performance, but not to show that our tool is in some sense better than the other ones. And we try to understand if the running time is as low as expected, and how does RPT behave in detecting one risk as a property tester. And we also provide some observations in how RPT behaves in detecting multiple risks. Okay. And we have 149 benchmarks from parallel work on risk detection. And we have one risk per benchmark, and we run 50 rounds on each trace for every two. Okay? So running time. Since we have 149 benchmarks, we bucketed the benchmarks into 5 buckets based on the execution size. And we do see that the running time of RPT doesn't grow proportionally as the size of the execution grows larger. Okay? But since we are only sampling constantly many, we would like to understand if the two is really only adding a constant overhead by analyzing events. So the total running time of experiment has 2 sections. Basically, the first section is sample time. which is the time we paid for every event. Namely, we need to pay something to determine if an event should be sampled. This is a cost paid for all the events, and that's why RPT's running time actually still grows as the size of the execution grows. And the other part is analysis time, namely the cost that we pay to analyze the sample event to determine if there is any risk. And this is supposed to be constant for RPT, but it's at least proportional for tools like Pacer and Fast Track. And we pick around 10 benchmarks that share the same parameter, which means RPT is going to sample the same number of events. And the size of these benchmarks, they differ from, say, 2 million to like 1.6 billion. And we indeed show that the analysis time is constant. Okay, and detecting one risk. So remember that in the experiment, RPT is designed to be a property tester with parameters epsilon equals to 0.01 and delta equals to 0.1. We do not expect the programmers to have a really accurate estimation on how the executions are far away from being risk-free. But rather, we want to know how this property tester works in general, and even on the benchmarks that are not that far. Okay, and we use the notion of riskiness as a proxy for epsilon, which measures the distance. Okay, and we define riskiness to be the number of warnings reported by Fast Track over trace length. And the metric we use to measure how successful RPT behaves is called success ratio. This measures how likely the tools can detect one risk in a run, and it is defined to be the number of runs that RPT detecting at least one risk over the total number of runs. Okay, and we show that actually in general our tool behaves pretty good for all kinds of benchmarks that are bracketed by different riskiness values. In most of the cases, it's behaved as good as Pacer as a property tester. Okay, it doesn't mean that we behave as good as Pacer as the risk detection tool. I'm not going to mention the other observations as they are not supported by our theory, but we have a pretty detailed experiment section in the paper. If you're interested, you can take a look. So the conclusion is that we presented a sound epsilon delta property tester that samples constantly many events to detect HB risks. And our experiment confirms that the running time of RPT is indeed as low as expected. And our artifact is rewarded with a reusable badge and is publicly available on the node. Okay, thank you.
Okay, so we have one question here. Please give your name and institution, please.
Thank you. My name is Rupak Majumdar. I work at the Max Planck Institute for Software Systems. I really like this idea of using property testing, but perhaps you could give me some intuition why this is so good. So if you have a trace of 1 billion elements and you have epsilon 0.01, this means that the property testing would require you change 10 million operations in order to be race-free. Mm-hmm. So now, how does this work so well? I would imagine that there will be, traces of 1 billion with only a very small number of reads and writes that conflict. But if it turns out that there are like 10 million things that conflict, this doesn't get, you see what I'm saying, right? So if your property testing is any good, then it has to be, 0.01 times away from all race-free traces, right? For a billion-sized trace, you would have to have 10 to the 7
Sorry,
traces.
can you speak louder? Sorry, I couldn't really hear that.
So what I'm getting at is that if you have a trace of a size billion and your epsilon is 0.01, then you would report a trace only when, or you're guaranteed to report a trace when you have 10 to the 7 traces, race conditions, right? Because that's the number of things that you change in order to be race-free.
Yes.
Now, this seems a very high number to me, right? I have a trace of 10 to the 9, of which 10 to the 7 elements relate to race conditions. Is there something in the benchmarks that makes this so?
Yes, actually, there are some very large benchmarks where Pacer still tends to find thousands of races, but RPT only is able to find, say, like 20 or 30 of the benchmarks. And all these informations are in the appendix. You can take a look. But the major idea is that a property tester does not necessarily behave horrible if the input is not epsilon far away. It doesn't have that strong mathematical guarantee that it is going to detect a race, we say with 90%. But it doesn't mean that it's going to behave totally randomly or in a very undesired way on traces that are, say, that not that far away. Actually, there is one example in the appendix that the size is around 2 billion with only 7 races. And we were never able to capture it. Okay.
Okay. Another question? I can try a little one. So I've seen that for your experiment, you take as input a non-randomized detector. Sorry.
I can't really hear that. Yes, sorry.
So in your experiments,
Yeah.
you build your detector using other detectors that are not randomized. Once you have done your sample, you use fast track, for example.
Yeah.
So if I have a dynamic data race detection, how difficult it is to use it with your approach to
Oh, you mean run our algorithm in an online manner, namely in a streaming manner?
So you have used Pacer and Fast Track.
Yeah.
How is it to use a third one? How, in terms of implementation effort, in terms of experiments, is it easy to change the detector that you
Yeah, it's
yes.
really easy. Yeah, our algorithm is actually very naive. You can see. You basically all you need to do is to find an algorithm that does uniformly sampling, and you can basically run whatever algorithm you want to run.
Okay. Thanks. Thanks again. Another question? We are a bit in advance. No. Okay. Thanks.
All right. Thank you.